Hello, and welcome to our Fluid Mechanics Open Lab presentation, where we will be comparing the performance of different golf balls.
Golf is one of the most popular sports in the United States, with millions of people who play. One important factor that affects every golfer's performance is the design of the golf ball itself. Differences in design can have a big impact on the distance that the ball travels, how accurately it travels, and how much control that the golfer has over it. One key feature that we can notice about a golf ball is that it has a dimpled surface. We will dive deeper into the effect that the dimpled surface has on the aerodynamic performance of golf balls. Our objective in this project is to analyze the aerodynamic performance of 3 of the leading golf ball brands: Callaway, Titleist, and Pinnacle. We will test the golf balls in a wind tunnel and compare the results to a ping pong ball, which has a smooth surface, to use as our control. Our goal is to study and compare the differences in wake size and wake formation of each golf ball and of the ping pong ball. To collect the necessary data, we will use a 5-hole probe to measure both the static and stagnation pressures at various downstream locations behind each ball.
The Open Lab was conducted in the low-speed open-circuit wind tunnels available to students at Potter Engineering Center. Shown in the depiction to the right, we see the direction of airflow as it goes into the test section. The test section measures 30.5 centimeters in width, 30.5 centimeters in height, and 61 centimeters in length. The wind tunnel is able to function at speeds ranging from 3 meters per second to 48.7 meters per second. However, for this experiment, we kept a constant frequency of 40 hertz, which is about 30.88 meters per second. The 5-hole probe was used in the lab to collect pressure readings at different locations around the test subjects. As its name suggests, the probe has 5 holes that each individually capture pressure readings. These readings are then used to measure not only the magnitude, but also the direction of velocity flow. The probe also has a high accuracy with results in about 0.1% of the true value, making this a suitable instrument for the Open Lab. The lab began by measuring the atmospheric pressure and temperature, which would later be used to calculate the air density. To measure the atmospheric pressure, we used a barometer, shown to the right, where the adjustment knob was first turned to move the pointer until it just touched the surface of the mercury, essentially calibrating the equipment. Then, on the top portion of the barometer, the vernier scale was adjusted so that its bottom edge aligned exactly with the top of the mercury. The atmospheric pressure was determined by reading the value where the vernier scale lined up with the main scale, and then adding that to the value where the main scale met the sliding 0 scale. Next, the temperature was measured using a thermometer. To translate the probe to various data collection points, a 2-axis probe transversing system was used to manually manipulate the X and Y positions of the probe. Encoders attached to each axis output these locations. The pressure measurements collected were recorded by the probe and then read by a temperature-compensated electronic pressure scanner, which output digital reading of the pressure for data collection. To collect and read all the data from the different equipment used in this lab, we used the National Instruments Data Acquisition System. In this setup, the system was responsible for reading pressure values from the pressure scanner and position data from the transversing mechanism. The test models for this experiment consisted of 3 golf balls, a Titleist, a Callaway, and a Pinnacle, as well as a generic ping pong ball. The support rod used to mount the models is a 3/8 by 16th square. So to be able to mount the golf balls, a 5/8 hole was tapped into them using a mill in the ME machine shop. As for the ping pong ball, due to the material, a soldering iron was used to make a hole of the appropriate thread size. Each model was mounted 4.5 inches away from the stand to keep data consistent. The balls were mounted in this way to simulate the conditions of a ball flying through the air while minimizing external forces that could affect the data. This configuration helps to ensure that the data collected is as accurate and representative as possible for meeting the experiment's objectives.
For our test plan, we have outlined the procedure as follows. First, we started by taking atmospheric measurements using a barometer and temperature with a thermometer. This allowed us to calculate air density later with these results on the experiment raw datasheet. Second, we prepared the wind tunnel by mounting each ball onto the stand, launching the appropriate LabVIEW software, and creating the data file for each respective ball. Third, we aligned the 5-hole probe 1.3 millimeters above the top center of each ball and zeroed the position so that we would have a uniform coordinate system for each of our tests. Using the experimental raw datasheet, we calculated the specific X and Y coordinates for data collection. Next, we set the wind tunnel to 40 Hz for data collection and scanned each point. We took over 100 points for each ball. Finally, we shut down the wind tunnel, removed the ball, used Aeroflow 2 software to convert pressure data into velocity data, and exported our results. This slide shows the wind tunnel setup for our experiment. It is important to note the mounting of each ball with the support rod and the position of the 5-hole probe. We kept this setup identical for each ball we experimented on so that our data would not be affected by inconsistent setup. For our test plan, we also have important test conditions that will impact our data. First, the atmospheric pressure was measured at 749 millimeters mercury, which converts to 99858 pascals. Our temperature was measured to be 21.5 degrees Celsius, which converts to 295 Kelvin. We used the air density equation, rho equals PV over RT, along with the ideal gas law to find air density. This air density was found to be 1.169 kilograms per meter cubed. We needed to make some assumptions to accurately collect and analyze data. These included that we assumed a uniform and steady flow, incompressible and 1D flow, constant pressure and temperature throughout, and balls as perfect spheres with dimple imperfections. The Reynolds number was calculated from the Reynolds number formula of rho VD over mu. From our experiment, we determined the range of Reynolds numbers to be from approximately 1 times 10 to the 5 up to 3 times 10 to the 5. Finally, we assumed the flow conditions to be a free stream velocity set by the wind tunnel frequency of 40 Hz. This is consistent with our assumed steady and uniform 1D flow across all of our tests.
Now, moving on to our results. Here, we have the velocity contour plots showing the wake regions behind each of the 4 test spheres, 3 different brands of golf ball, and 1 ping pong ball. Starting with the top 2 plots, both show relatively narrow wake regions immediately behind the ball. The bottom left plot shows the 3rd golf ball. Its wake pattern is very similar, but it is noticeably a slightly larger separated region that persists further downstream. This is at the limit of what we could measure, so it is not super critical and does not have a large effect overall. The bottom right plot shows the ping pong ball by comparison. The difference is very easy to see. The wake is much larger and less structured, indicating an earlier and more complete flow separation. Without the surface roughness created by dimples that cause an early transition to turbulent flow, the boundary layer stays laminar much longer, and the low total energy of that flow makes it much easier to separate earlier, leading to an ultimately larger wake that produces more drag. Overall, the results matched what we expected. The dimpled surface on the golf balls, they help control the boundary layer, they delay separation, and they reduce the size of the wake, which ultimately lowers drag compared to a smooth ball, like a ping pong ball in this case. To summarize, the 3 major brands of golf balls had very similar wake shape, which was expected because of their outwardly very similar geometries, roughly similar dimple sizes, roughly similar spacings, and the results were in line with what we expected, that there was no major drag-based difference between any major brand of golf ball that we tested. However, the ping pong balls did have the significantly larger wake, which indicates a far higher overall drag than the golf balls, which this was likely due to earlier flow separation caused by the laminar flow over the golf ball or over the ping pong balls having a lower average energy, meaning they had a much harder time sticking to the back face of the golf ball or the sphere in general as it flowed through the air. The golf balls having the turbulent flow over the entire surface creates a higher mean energy, which allows the air to stick more readily to the backside of the ball, reducing its wake size. Which ultimately does have effects in golf, which is why golf balls have dimples, because it does allow them to fly significantly further than a smooth counterpart.